Okay, thank you, Naveed, for the intro, and Chuchu for arranging this visit. So I'm really excited to talk to you today about some recent work I've been doing at the interface of machine learning and control. Specifically, I've been looking at trying to figure out when is it a good idea to collaborate in order to accomplish a given task. So this is work that has been really led by one of my PhD students, and more recently Leonardo Tasso, and thank you to NSF for funding this. So the problem that I'm interested in is that collaboration in general seems like it should be a good idea. Right? It seems, okay, two minds are better than one. But I mean, if you think back to when you were a student, right, and you were in an undergrad lab, and you had your lab partner, and you just started working, and then in comes the guy 10 minutes late, slightly hungover, hasn't done any of the prep, and now he's going to work with you, right? Is that really a collaboration? Is that going to help you? Probably not. So the question is, when does it pay to collaborate, and can we be sort of slightly precise about what we mean by that? So the way I'm going to frame this is as a federated learning problem, and essentially we're going to follow the same workflow, and we're going to see this in two, maybe three different contexts. The idea is that there are going to be a set of systems generating data individually, and the idea is that individually you're going to train and learn a model on your own data. You're then going to pass your model to a server. The server is going to aggregate or perform some statistical computation across all models, and then broadcast that sort of global model back to all the agents. The agents are then going to use that as a seed point to run more local optimization. And you're going to go through this process quite a few times. And the idea being that if I have different agents in different environments, then I have the advantage of picking up knowledge from a different environment that I wouldn't have otherwise got myself, or it might have taken me longer to explore that area of the search space. And the caveat here is going to be that the systems that are generating the data aren't necessarily identical. Okay, they're going to be related, and we'll quantify what that means. But the question is, can we obtain a model that is meaningful in any sense? How close to optimal is it? And what is the price I pay for the fact that the models that are the systems that are generating the data aren't the same and operate in a different environment? So we're going to look at this in a system identification setting. So that's control speak for learning a linear model. Yep. Or maybe we're not. Okay. And then we're going to look at, okay, well, once I've got this global model, and the idea is once you've got the global model, then you can go away and train locally to sort of fine-tune it. Once we see what the achievable performance is, we're going to look at how we can improve that and sort of better design a personalized model for what I would like to do with it. And if time permits, and it probably won't, we're going to look at how this framework can be applied to learning an optimal controller directly from data without building a model. So I assume most people know what federated learning is. In fact, probably half the people in the audience have written a paper on federated learning by this point. But the idea is it is a method for large-scale optimization where essentially you have multiple sources of data. The data stays local, you train locally, and then you aggregate models. Data never leaves the device, so data is never transmitted, only models. And the idea is this should, A, give some sort of privacy guarantee, but B, communication is really a bottleneck if you need to send massive amounts of data between sources. And the idea behind it is really to take into account the fact that different agents there'll be heterogeneity amongst the data sources. It might follow different distributions, there might be different volumes of data at each location, and there might even be different compute resources along at each agent. But none of this should matter. The idea is we would like to produce a global model that somehow takes into account all of these different data sources and accounts for all of this heterogeneity. So the idea has been around for quite a long time. In fact, Google have been using it for word prediction on their mobile phone devices. I think it was around 2017 when this technology was first deployed. And the cartoon idea is, okay, in the centralized setting, all the data is in one location, and we might want to learn a model, which in this case, let's just do a simple linear regression. In the centralized case, okay, that's pretty straightforward. But what happens if now the data, now here we've got 3 different data types. The idea is each, the purple, the red, and the blue will each learn their own model, or at least run a few rounds of learning. It will send their model, so in this case, a gradient and an offset. You average it, you broadcast, you repeat, and if you're lucky, the overall learnt model will look something like this, even though the data, at no point was this data shared. Obviously, this is a very stylized example, but that's kind of the idea. Okay, we're just going to keep learning, averaging, repeating. So why is this actually relevant? Well, at least in the EU now, there are very, very strict laws on what data can be sent. Right? Data privacy is a really big deal. The EU's GDPR essentially makes it very, very difficult to send data outside of the EU. California implemented similar legislation based on the European standard, and it's coming to other states slowly. So even if communication wasn't an issue, data ownership is becoming more and more of a big deal. And so this idea of federated learning, where the data never leaves the host, is something that we need to start considering. So the generic problem, or the generic federated learning problem, is going to look something like this. I have n agents that are each going to, this fi might be some minimize your own empirical loss function, for example. We're not going to assume any convexity on the f's, but we are going to assume that G is convex, but not necessarily smooth. So this could be an L1 regularizer or something that's going to shape the output. And as I said, the data, so the local data isn't going to move. And so, again, there have been tons of papers written on this, and I'm going to talk you through this very simple example of an algorithm we've developed, not because it's the greatest algorithm, although it is fantastic and you should definitely use it, but more because I want to sort of emphasize the framework that we're then going to shift to for the system identification part of the work. So our contribution is really that we don't assume that the gradients are bounded, and neither do we assume that the gradients coming from different agents are bounded. So as I said, there are no shortage of algorithms. Fed average was perhaps the first one, where essentially you run a few steps of stochastic gradient descent locally, and then you send that to the server, average, and repeat. Martin Wainwright here quickly figured out that actually you can, whilst this algorithm seems to work well empirically, you can actually converge to the wrong stationary point that bears no resemblance to any of your data. So he created Fed split, and then about 20 other algorithms since, with different twists, putting in extra assumptions, removing others. And so our contribution to this sort of soup of algorithms is Fed ADMM, which is essentially taking the dual of Douglas-Ratchford splitting in a federated sense. So we're going to rewrite the problem. I'm not sure what this little arrow, why that's there, but this essentially we're going to rewrite this in consensus form. So we're going to introduce this new vector x bar, and we're going to force each xi to equal x bar. So x bar is the consensus variable. X is going to be the local copy of the data of the variable, and we form this augmented Lagrangian. Okay, so everything is sort of exactly as you would expect here. We've got a smoothing parameter, dual update, and the algorithm looks something like this. On the client side, so the server, first of all, the server is going to select a subset of clients. So there's no implication that every client needs to participate. Clients can drop out. We're going to randomly select a subset of clients. It's going to receive x bar from the server. This is the seeding point. and it's going to minimize its Lagrangian. It's going to perform a dual update. It's then going to update its own variable, and then it's going to send the difference between its last output and the new update back to the server. Every client that's sampled is going to do this. Now, there's a few things to pay attention to here. In the algorithm, we're not insisting that you optimally minimize this Lagrangian. You can only, if you want, just take a few steps. A minor improvement is fine. So essentially, you're allowed to specify an epsilon. Each client has its own epsilon. In each round, that epsilon can be different, and you're just going to run whatever minimization you like in order to hit this epsilon, and then you're going to bail out. Okay, iteration K, only a subset of the clients need to send those local updates. That subset is going to be different at every iteration. And the seeding comes through the initial X bar. On the server side, well, not much happens, right? It receives all the X's from the clients. It computes an average. And if there's a regularizer in the mix, so if G isn't 0, then it takes one proc step, and then it selects clients for the next round and broadcasts the new X bar, and just keeps repeating through this process. Okay, for capital K server-side iterations. And so the analysis, or at least what you can show, is that, and this is the simpler version where there's no regularization. The regularized version goes through with a few extra constants, but essentially you can hit a stationary point after k iterations that is bounded by this slightly ugly-looking term on the left. I'm just going to break this down. The term 1, this is the initial optimality gap, right? This is what you would typically expect to see in a standard descent type algorithm, right? It's bounded by the distance from your initial point to the optimal point scaled by the iteration. This point 2 on the right, this is now the cost you pay for terminating early. Okay, it's scaled by the number of agents n, but it's essentially the running cost of all of the errors for bailing out early and not running until you've properly minimized the Lagrangian. The effect of partial participation, that is that not all agents have participated in the round, is absorbed into the constant C1 and C2 here, and you can write it down. It's not particularly illuminating. But the point of this proof is to kind of get it, what we're going to look at in future results is what is it you pay for either dealing with approximations or introducing uncertainty or heterogeneity into the problem. And in this case, clearly it's this term 2. This is the cost of doing business in the federated setting. So you can rewrite this, and essentially you can figure out what the error is going to be after a fixed number of steps. And just so you believe me when I tell you that this works, we've got 2 plots here on the feminist data set, where on this graph you can see as the number of participating clients in each round increases, the accuracy increases, and simultaneously the loss decreases more quickly. Okay, so that's the federated learning setup, and this setup we're now going to port to control, where we're now going to try and learn a linear dynamical system model from data. Okay, so SysID, you're given data, you would like to come up with a mathematical model that downstream you're probably going to do some control with. This is also useful in adaptive control, or if you just want a differential equation model, you don't need to do this just for control. So we're going to go to the centralized setting first. I'm going to tell you what the sort of state-of-the-art result is in terms of sample complexity here, and then we're going to look at how federating the approach can help us out. So we're going to assume that we have a discrete time system over a finite time horizon, going from t equals 0 to t minus 1, where the ground truth system is parameterized by A star and B star. Now, this system, we're going to assume that there is zero mean noise. It's IID across time with variance sigma W. The control signal U, likewise, we're going to assume is a zero mean Gaussian with some variance. And what we're going to do is we're going to run the system for t time steps, then we're going to reset it and run it again. And we're going to do this capital N times, and we're going to collect our data, x and u, at each time. So we parameterize our model by a star, b star, we call that theta, and we can rewrite the system this way, where z is nothing more than the state and the input stacked together. We're going to collect all of our rollout data. Okay, so remember we have capital N simulations, and we're going to form these block matrices that store all the data. So X stores our state information, Z state and input, and W the noise. And so this relationship is perfectly characterized in matrix form by X equals theta Z plus W. And remember, W is the noise, so it's not difficult to see that a least squares that we'll use sort of the obvious thing to do is come up with a least squares estimator for theta. Okay, so we want to find theta that minimizes this quantity, and we'll call our estimate theta hat. And so Sarah Dean and Ben Recht and Nick Matney and a few others showed that this estimator, essentially the worst case error between the ground truth A and ground truth B and the B that you estimate is bounded by this quantity. And if you look at it, well, there's a few things to pick out. First of all, that this thing scales with 1 over the square root of the number of trajectories that you collect. So this sort of tells us that the more trajectories we collect, well, this is going to push down on the error, so we should get a better estimate. On the left-hand side, this sigma sub t, well, this is the covariance of the state at time t, which if you work out what that actually is, it's this slightly ugly-looking expression here, but actually GT transpose, this is the controllability Gramian from the input to the state, and FT transpose is the controllability Gramian from the disturbance to the state. So what this result tells you is it's now the minimum eigenvalue of this appearing in the denominator, is it tells you that systems are difficult to control, will require more samples in order to get a better error. So there's a system theoretic interpretation, right? Not all systems are equally easy to identify a model for. One caveat I should say in this result and in our results, even though you run the simulation from time t equals 0 to time t, in order to get statistical independence, you only actually use the state taken at the final time step, which is kind of wasteful. You can bootstrap to improve that, but the theoretical results assume that you only use the final time step in the estimator. Yeah. Okay, so we're going to move to the federated setting, and first I'm just going to describe where the data comes from, and then I'm going to tell you exactly what the problem looks like. It's a little bit tedious, it's a bit of bookkeeping, but essentially now we're going to assume that we don't just have one system, we have M systems generating data. This is the noise profile, which I didn't specify on the previous slide, but everything is mean 0 with a specific covariance. And each system generates Ni rollouts worth of data. Now, we're going to assume that the systems are not the same, right? So A3 star is not the same as A2 star. Okay, but we do need to quantify the heterogeneity in some sense. So we're going to assume that there is a bound epsilon that upper bounds how different any of the A's and B's can be. Now, you don't need to know this value of epsilon a priori. That's not the point of the epsilon. The epsilon is just going to show up at some point in the convergence proof, and this is sort of a proxy for how different the systems are going to be. So the objective now is to learn one model from all the different data sets, right? So even though the data is generated by different systems, we only want one model. So you can, from a practical standpoint, you can imagine you have a bunch of drones made by the same manufacturer. So their flight dynamics should be somewhat similar. They'll be manufacturing defects, so they're not going to be identical. You may put on your own payload on each of these, which will again affect the dynamics. And they're going to be run in different environments. One might be put in a wind tunnel, one might be outside, one might be in perfect lab conditions. But still, we would like a model that is a good fit for all of them. Okay, so this assumes that the underlying drone in this case is kind of similar. This isn't going to work if you try learning on a submarine and an aircraft, right? That's doomed to fail before you begin. But if there's some sort of similarity, then maybe we can leverage this. So essentially what we want to do is solve this least squares problem, but we want to do it in the federated setting where the theta, everyone learns their own theta locally and then sends their theta I estimate. Some averaging is done, and we sort of go through this process again. So there's something that's a little bit, any of you who controls people will probably be quite uncomfortable with this notion of similarity of systems, right? There's no system theoretic no notion of any systems theoretic properties captured by this epsilon. A simple example is these two systems, systems 1 and 2 here. System 1 is open loop stable, system 2 is unstable, okay, but the epsilon on the A is going to be very small there. Similarly, the system 2 has the control input. This is going to be a difficult system to control, at least relative to system 1. So the question is, are these two systems really similar? In our metric, they are, which isn't ideal. So some possible fixes, and students are looking at this at the moment, are to replace this epsilon bound on individual matrices with either a system norm or potentially a closed loop gap metric type of thing. But that it kind of unnecessarily complicates things for the story I'm going to tell today. So the algorithm, and this is going to look very similar to the federated learning algorithm that I showed earlier, looks like this. We start off with an initial model estimate. We're going to go through capital R rounds of outer averaging. We're going to select a subset of our M clients. And now this is actually a proto-algorithm in the sense that you can drop in whatever federated learning scheme you like. I'm not going to specify that. I will specialize it to two specific examples later, but you can put in any client, any update model you like in here. So this could be run 20 steps of stochastic gradient descent, for example. It could be Douglas-Ratchford, but it could be anything you want to put in here. And then you're going to send your model back, and the server is going to do nothing more than average and return it. Okay, so it's exactly following the sort of the scaffolding from the federated learning setting. And what we can show is that with high probability, the estimate, theta bar, is close to, in the worst case, each of the ground truth AIs and BIs, and it's bounded by, again, this admittedly ugly looking term, but we're going to break it down into two components. Okay, this constant 1, this is nothing more than the sum of the state covariance matrices over time. But this thing is scaled by 1 over, and remember in the previous setting it was 1 over the square root of the number of trajectories. Now it's 1 over the square root of the sum of the number of agents multiplied by the number of trajectories. So this is where you're seeing the speed up. Okay, this is the benefit you get from using multiple agents' data. So this is good. But now we've got this second term, and this thing is, again, it's just a constant. And sorry, I should say, again, we have a controllability type measure in the denominator, but this thing is now scaled by epsilon. Right? This is how different the systems are. So if the systems are really different and epsilon is going to be large, then it's likely that this term is going to dominate this term. Okay, so if the systems are really different, then collaboration isn't going to help you much. Okay, so there's a regime where epsilon is small enough that you actually get this speed up. Okay, so one way of interpreting this is you get the speed up you want multiplied by how good the signal to noise ratio is, because that's really what the control, this 1 over the minimum eigenvalue of the controllability Gramians is giving you, plus some linear term in the heterogeneity of the problem. Okay, so when epsilon is small, we were able to improve our model performance from 1 over square root of the number of rollouts through to 1 over the square root of the sum of the number of agents multiplied by the number of rollouts. So we can now drop in your favorite federated learning algorithm. So fed average, and this is just run m steps of stochastic gradient descent, will, if you specialize our error bounds, gives you this form, right? So you've still got the C1 over the speed up plus your epsilon times C2, but now you've got this 1 over K is the number of K is the number of agents, R is the number of rounds. So fed average perhaps being the most simple algorithm, you get this constant 1 over KR term you have to deal with. Fed lin, this was developed by Aritra Mitra and George Pappas. Now this bound looks better, but you pay more. This is a more expensive method. This uses a memory, so a sort of momentum type method, which you're now able to get a slightly better term on the left-hand side, but the error constants are still floating around. Okay, but the speed ups are both still there. So take your favorite federated learning algorithm, drop it into this, and you can see what sort of speed up you get. So the numerical experiments, we generated nominal system A0, B0 given by this matrix. Okay, so this is actually open loop stable, but it doesn't necessarily need to be. And we're going to generate a family of systems by introducing these perturbation matrices V and U and scaling parameters gamma 1. And we generated up to 100 different systems. And you can see on this plot, this is what happens as we increase the number of agents. You see kind of what you'd expect to see. The error decreases. On this plot, this is now the number of rollouts. Okay, so Ni is the number of rollouts for the ith system. Again, the Ni's don't need to be the same, but just for simulations and to keep track of things, we'll keep them the same. So again, as you increase the number of rollouts, you can see that the error starts decreasing at a much more favorable rate. And here we're varying the heterogeneity, right? So epsilon equals 0.01. The systems are pretty damn close to each other. Okay, by the time you get to epsilon equals 0.75 for a 3-state system, there's a certain amount of variance, and you can see that the performance does exactly what you expect it to do. As the heterogeneity increases, the system performance decreases. Okay, so the problem, well, not the problem, but something that or a question we should be asking ourselves about these sort of results is, okay, so I can get one model out. I can get a global model out, even though I've got these M systems, but if I look at the error bounds I get, I have no control at all over this heterogeneity term, right? There's nothing I can control, Right? I can't, carrying out more simulations doesn't help me here. I'm kind of stuck with that. So is there any way to beat or to get around this problem? And so what we thought about it, and we thought, okay, well, if I really do have 50, 100, 200, 500 different systems, how different are these systems actually going to be, right? Am I really going to try a sort of collaborative control experiment with systems that I don't know, that I want to learn a model of, that are really different? And the answer is probably not. But you could imagine a setting where I have a group of drones that I bought from one manufacturer, a group of drones that I bought from another, a group from another, or autonomous vehicles, different manufacturers, or with different, or any autonomous vehicle with different payloads, for example. And there, the idea of having one model for my two different drones doesn't necessarily make sense. I'd still like to have the benefit of collecting data from them, and maybe I can use that in a useful way. But the one model isn't maybe the best way to go about formulating the problem. So let's try and get some personalization in here. Let's try and tailor our model to let's try and produce models that are specific to different subtypes of models. So the advantage of this is, well, if in all of the data I'm collecting, I can find models that are more similar to each other than not, then I can do my collaborative learning with those guys and ignore the ones that have a higher epsilon value. But that comes at a price, right? If I identify my model as belonging to the wrong cluster, then I've basically I've sort of taken a model that has a high, or two models that have a high epsilon value, put them together, and so if I get it wrong, then maybe I'm going to slow down the learning. And so what we're proposing is a clustering-based method, which is going to simultaneously figure out which is going to simultaneously figure out what cluster this data source belongs to, assign it to the cluster, then within the cluster learn, then it's going to send that estimate to the server. The server is going to do some averaging in sort of a very obvious and intuitive manner, and then we're going to allow to recluster. Maybe we got something wrong. Let's now see, after we've averaged, do we still think that we belong to the cluster we've been assigned? If not, assign it to another cluster, and then do some more local learning with the new clusters, and repeat. Problem is, if we incorrectly classify, then we're going to slow things down. So the cartoon is, well, I'm not just trying to identify fruit anymore. I would like to identify specifically strawberries, I don't know, apples, and I think those are meant to be pears, I think. So the setup is going to be very similar, right? We still have M systems generating data. Okay, the data sets look exactly the same, but now we have K, each one of our M data sets is generated by one of K system types. Okay, what K is, in order to make this not a completely meaningless problem, K has to be much less than M, right? We need to have fewer system types than amount of data that we're collecting in order for this to make any sense. And so each one of these K system types we're gonna label from C1 to CK. These are our clusters. And each cluster is going to be defined by a specific AJ, BJ pair, where the AJ corresponds to one of the AIs and BIs from the generated data set. And we're going to define theta sub j as, it should be AJ, BJ. So the objective then is, given these M data sets, can we partition the data sets into clusters where the similarity within clusters is greater than the similarity out of cluster, then learn a common model within that cluster and do it in a way that would be give us a performance advantage than had we just taken all of the data together and tried to learn one common model, or had we just taken a centralized approach, collected all the data and run a single model. The challenge is we don't know what cluster the systems belong to. Okay, and remember, even because of the noise in the model, even if the A and the B's are the same, the noise profile is going to be different. So the data sets aren't identical anyway, but they're going to be related. So we need to get away from the fact that misclassification may hinder progress. So we need some assumptions in order to do this. So let's assume we have 4 clusters, ground truth clusters. And we define 2 parameters, delta min and delta max. Delta min is going to be the distance between the closest 2 clusters that exist, and delta max is going to be the maximum distance between 2 clusters. And what we're going to see is that clustering is easy when the minimum separation is large. Okay, if you've got a lot of clusters and they're all very, very closely packed together, then it's going to be more difficult to figure out which cluster you actually belong to. Okay, so ideally we would like a large delta min. Okay, specifically, we're going to need a radius essentially around these clusters that there's the largest sort of ball we can put around these clusters such that the balls don't interact is going to be very, very useful to us. So we have to start off with an assumption that our initial estimate for the cluster is bounded by this quantity. Okay, so what this is effectively telling you is that the clusters you're going to initially assign things to has to be slightly better than a random guess. This isn't going to work if you have no idea and you just randomly assign. Okay, we're also going to assume that the number of samples and this distance is sufficiently large. You can write down explicitly what these things are, but they're functions of the data of the problem. They're not particularly interesting. But this is essentially delta min being sufficiently large has to satisfy roughly, it's a function, this is where the delta max comes in, but it's essentially an exponential of taken over problem data. So I'm going to give you the algorithm in cartoon form, and it's a little bit more intuitive than writing it down. But essentially we have our M data sets, right? This has been generated from our M systems. We assign each data set to a cluster, and we do it via evaluating this norm minimization. Okay, so we figure out, okay, which of the theta models is my xi zi pair closest to, and we assign based on this clustering metric, we assign it to the minimum cluster. So it's really simple. You just compare to every model you've got, assign this data set to whichever fits better. So we come up with an initial clustering. And then, so for example, in cluster 2, what we do is we take our cluster model from the previous step as the starting point, and we run just one step of gradient descent. Okay, so that's what's captured down here. And moreover, the one step of gradient descent is done locally at each agent. Okay, so you go through for all M agents, you assign them a cluster, then at every agent you take one gradient descent step, and then you send every agent in cluster 2 sends its updated step to the server, and the server averages, the server managing that cluster averages it. Every one of these does it, every cluster repeats this process, only taking one step. and then we go back, we reseed to do more clustering, and we keep taking these steps. You can modify this to take multiple gradient descent steps, but you've got to be very careful. It's quite, maintaining statistical independence gets a little bit tricky, and the expressions get considerably more complicated, so we haven't done it, we haven't shown it here, but in principle, you can do this. And then phase 2, okay, well now we run our clustering metric, and because our estimates for the theta may have changed, then the clusters may have changed. So we now reassign, and we run this process again. And we can show that well, let me show you what we can show. So this is the algorithm, the details, I think the cartoon covers everything, but what are the theoretical guarantees from this result? Well, first of all, we can quantify the probability of misclassification. Okay, so what is the probability that we assign dataset J to cluster J prime, and that's incorrect. Okay, and essentially, if you look at this thing, well, first of all, it's an exponential, so this is going to be very well behaved, and the coefficient in here is the state dimension multiplied by the number of trajectories, the number of rollouts. Okay, so this does tell us that the more data we have, the less likely we are to misclassify. So the overall convergence result looks like this. After our outer iterations, that's after our attempts of reclustering, then for every cluster, we have a model whose error, the difference between the error from the algorithm and ground truth, is upper bounded by this thing. Okay, now the details aren't overly important, but what we see is that this constant 3 is scaled by the number of trajectories present in the cluster. Okay, so now we're getting speed up within the cluster, plus now an exponentially decaying term that is a function of something we can control, the number of trajectories, as well as a few other problem parameters. And for R sufficiently large, and sufficiently large here I don't mean asymptotically, I just mean greater than 4 or something, relatively well behaved. Not going to give the specific details on it, but essentially for R large enough, we see that this bound holds independently of how well we were able to classify initially. Okay, so you don't need a fantastic initial guess on the clustering. So if we compare this to what we were able to achieve in the federated sysid case, right, we had no control over here. We got the speed up from our M agents, but we had no control over this term. If we combine clustering with learning, then now we still have the benefit of the speed up within the cluster. Okay, it's the same signal to noise ratio that the constant that appears on the left. But now we have this term on the right, and this is really a function of the misclassification. And we have control over the misclassification, and moreover, the misclassification decreases exponentially. Okay, so we're in a much better situation here. Specifically, exponentially in the number of trajectories we collect. So again, you can see the advantage of collaboration on this top plot. We had 50 systems, 3 clusters, taken over 50 time steps. On the top graph, this is each of the 3 different models. If you didn't apply clustering, what you would get, and on the bottom graphs, this is now if clustering is taken into account, and in each case you see that the error substantially decreases. You get rid of this sort of constant bias offset for essentially fitting a bad model to the data. And you can see as well that the number of misclassifications that occurs decreases exactly as the theory tells you to, right? R is the number of outer iterations. And so as we increase the number of rollouts, you see that the number of misclassifications really does drop off very, very quickly. So there's a number of extensions that we're trying to put together specifically on the clustering. So the one thing we would like to get rid of is the fact that within the clusters, we assume that the models have to be exactly the same. Right? So if we have 3 system types, and therefore we have 3 clusters. It would be great if we could have, okay, we have 2 base models and we cluster within a ball of epsilon uncertainty. Give us sort of an extra degree of freedom. And again, getting the system heterogeneity in some sort of system theoretic context would I think be really useful. I'm going to end very briefly by telling you about some work we've done now on data-driven control. And I think I'm running out of time anyway, so this is really just going to be a cartoon sketch. But the idea is now, instead of building a model and then doing control based on the model, let's do control based immediately on the data, and we can do this using a policy gradient type method. And so the setup we consider is exactly the same, m different systems, certain level of heterogeneity, and we would like to compute a single LQR controller that stabilizes and minimizes quadratic performance for each system. So this kind of looks like an H2 type optimal control problem, but this isn't a classical control problem, and we were surprised there were no sort of off-the-shelf solutions to this, which also made it harder when you go to the data-driven version, because there are no specific algorithms you can just sort of bootstrap off of. So the policy gradient in the centralized setting just says, okay, well, I'm going to basically run gradient descent on my control parameter. Okay, so I'm going to treat k as a parameter, and I'm going to do gradient descent on it. And so when I have a model, I can write down exactly what the gradient is. Now, this problem isn't convex in the controller variable k, but Mariam Fazal and co-authors showed that there's a gradient dominance property that allows gradient descent to converge to the global minimizer, the global optimizer, despite this lack of convexity. So we were trying to work out, well, can we do that in the federated setting? Now where we've got multiple systems and the gradient dominance condition does not carry over to the federated setting. And in the model-based setting, obviously we don't have access to the gradient, so you need to use some sample-based zero order method, of which the details I'm not going to go into because I'm just going to point you to the paper. But essentially, it's not a big issue. But again, this is our algorithm. It looks exactly the same as everything I've shown you already, just now move to the control context, right? We're going to do locally, we're going to learn a controller based on data we sample or we simulate. We're going to send an average to a server. The server is going to average it, broadcast it, and we're going to repeat. It sounds very, very simple, but showing that this thing works in practice is incredibly complicated. First of all, you need to assume that there is an initial stabilizing controller that stabilizes all the systems. Well, you kind of need, in a standard robust control setup, you would need that anyway, so that's not too much of an issue. Finding it technically is, but we can hedge around that. You need to, there's a few other technical assumptions which I'm going to gloss over, but what we were able to show is that after every round of averaging, right, so everyone computes their own local controller, obviously that's going to be stabilizing, but the average is stabilizing for every system. Okay, so even if you can only run this for a few outer loops, you're still going to have a controller that stabilizes each one of your M systems. We can also show that after a finite number of steps, we can bound the optimality from the globally found controller to every one of our local systems is bounded by this offset. So these are just problem parameters, and this B is a ball of radius that is a function of epsilon 1 and epsilon 2, which defines how different the A and the B matrices are. And this is a hard limit. We can't expect to converge to a globally optimal controller. We can just get within a radius of it, because the heterogeneity actually keeps us away from global optimality. So this was very new. We put this out a few days ago, which is why I wanted to jam this in. So with that, I'm going to go back to my conclusions, and thank you all for coming. And all the papers are available on my website. There's lots of, again, this was mostly ideas rather than technical details, because I think this is an area of work that is, or an area of learning that is underutilized at the moment in control. So we'd love it if more people jumped on and started working on some of these ideas. And so with that, thank you.